Before you watch a single second more of this, I want you to do something uncomfortable. Look at the nearest window, the nearest lamp, the nearest source of light in the room you're sitting in right now, and accept a fact that no amount of intuition will ever make you feel true. The light hitting your eyes at this exact moment has not aged. Not a second, not a millisecond, not a single tick of any clock anywhere in the entire history of the universe. That photon left its source and arrived at your retina in zero time according to itself. Not according to you, according to it. This isn't a party trick or a Wikipedia footnote. It's a structural feature of reality that quietly dismantles the way you think about the past, the present, and the thing you call now. Notice something before we even build the argument properly. You already trust a version of this claim every single day without knowing it. GPS satellites orbiting Earth carry atomic clocks that run measurably faster than clocks on the ground because they're moving at high speed and sitting in a weaker gravitational field, and both factors shift how fast time passes for them relative to you. Engineers correct for this daily, inside the software of the navigation app on your phone, using the exact same relativistic mathematics we're about to walk through. Time dilation isn't a thought experiment reserved for lecture halls. It's a correction factor running quietly in your pocket right now. Here's the claim in its bluntest, compressed form, before I earn it properly. Light emitted at the birth of this universe, and light emitted a nanosecond ago from the bulb above your head are, from light's own path through space-time, exactly the same age, 0. The cosmic microwave background, the oldest light we can observe, the afterglow of an event that happened 13.8 billion years ago by our clocks, has, along its own invariant path, covered no measurable interval at all between then and now. It is simultaneously newborn and older than every star in the sky. Before I walk you through exactly how that's calculated, hit subscribe now, because this channel goes deep into exactly this kind of physics, one honestly checked argument at a time, and I don't want you missing where this leads. Drop your location in the comments. I read every single one. I want to know who's watching this, from where in the world. And if this unsettles something you assumed was simple and settled, a like and a share help, this reach someone else who'd get pulled into it the same way you just were. Let's talk about what we're actually doing here, because you deserve to know the method before you trust the conclusion. We're not going to lean on authority or say, trust me, I'm a physicist, or hide behind a credential. We're going to walk through the actual structure of the argument, the same one that falls directly out of Einstein's 1905 paper on special relativity, and you'll be able to check every step yourself afterward. If a claim can't survive being shown its own working, it doesn't deserve your attention, and neither do I. Start with proper time, because everything else depends on it. Proper time is the time experienced by an object along its own path through space-time, measured by a clock actually traveling with that object, different from coordinate time, the time measured by an outside observer watching that object move. These two clocks don't, in general, agree, and that's not a flaw in measurement, that's the actual geometry of space-time doing what it does. The relationship between them is governed by the Lorentz factor, and here's the part that matters most. As an object's velocity approaches the speed of light, the rate at which its proper time advances, relative to an outside observer's time, shrinks towards 0. Not slows down a lot, shrinks towards 0. At the exact speed of light, the mathematics gives you a proper time interval of exactly 0, for any finite amount of coordinate time an outside observer like you experiences. Picture it in stages, because the jump from slower to 0 is where most explanations lose people. A jet crossing the Atlantic experiences proper time almost, but not quite, identical to someone standing still on the ground, a difference measured in nanoseconds, confirmed experimentally by flying atomic clocks around the planet and comparing them afterward. Push the speed up to a meaningful fraction of light speed, the kind particle accelerators routinely produce for unstable particles like muons, and the dilation becomes large enough that a muon which should decay in millionths of a second survives long enough to reach the ground from the upper atmosphere, purely because its internal clock runs so much slower relative to ours. Push the speed all the way to the limit, light speed itself, and the dilation factor doesn't just get large, it goes all the way to 0. No intermediate step at the very end, no diminishing return, just a hard mathematical wall where the proper time interval vanishes completely, no matter how much coordinate time you or I experience while it happens. Now I want to do something most videos on this topic skip, because it's inconvenient and it complicates the clean narrative. Photons do not technically have a valid reference frame the way you and I do. You cannot construct a proper Lorentz transformation that puts you in the rest frame of a photon because the transformation itself breaks down at exactly light speed. Physicists will correctly tell you that asking, what does the universe look like from light's point of view, is a category error, division by zero dressed up as a thought experiment. I'm telling you this not to undercut the argument, but because intellectual honesty means showing you the crack in the foundation before building on top of it. Here's why the conclusion survives anyway. You don't need a photon's reference frame to observe that the proper time interval, calculated along a null geodesic, the actual path light takes through spacetime, is exactly zero. That's not a frame-dependent interpretation. That's an invariant. Every observer, using every legitimate coordinate system, calculates the same zero. The spacetime interval between a photon's emission and its absorption is null, zero. That's not us imagining what light experiences. That's the geometry of the path itself having zero length in the relevant sense. The controversial part, where physicists genuinely push back, is describing that zero as something light feels. The uncontroversial part, the rock-solid part, is that the interval is mathematically null regardless of who's measuring it. Keep those two boxes separate as we go. An uncontestable mathematical result, and a contestable interpretation of what that result means for concepts like experience and point of view. Because collapsing that distinction is exactly how good physics turns into bad mysticism online. Now let's connect this to cosmology, because light doesn't age is a fun fact right up until you connect it to the actual structure of the observable universe, and then it stops being fun and starts being genuinely strange. Every photon reaching your eyes from the sun, from a star 4 light-years away, from the cosmic microwave background 13.8 billion light-years away, has traveled along a null geodesic, and along that path, by the invariant calculation, zero proper time has elapsed. But from your reference frame, wildly different amounts of coordinate time have elapsed for each one. Light from the sun took about 8 minutes to reach you. Light from the cosmic microwave background took nearly the entire age of the universe. Same zero along the photon's own path, wildly different numbers along yours. Which means that when you look up at the night sky, you're not looking at the universe as it currently is. You're looking at a patchwork of radically different moments in cosmic history, layered on top of each other, each photon carrying information from a different point in time, all arriving at your eyes simultaneously, all landing in your present tense at once. The star you're looking at might not even exist anymore. The light left it thousands of years ago, but the photon itself, by its own null interval, made the entire journey in zero time. There's no journey in the temporal sense from the photon's own calculation, just an emission event and an absorption event connected by an interval of exactly zero. There's a detail that makes the cosmic microwave background case stranger still. That light isn't just old, it's stretched. When it left its source in the hot, dense, early universe, it was high-energy radiation, closer to visible or ultraviolet light. By the time it reaches a detector on Earth, the expansion of space itself has stretched its wavelength out into the microwave range, a phenomenon called cosmological redshift. The photon didn't just travel an enormous coordinate distance while accumulating zero proper time along the way. The very fabric it traveled through has been stretching underneath it the entire time, in the reference frame of everything that isn't light. And yet the null interval calculation doesn't care about any of that stretching. It stays exactly zero regardless of how much the wavelength changed, regardless of how much the universe expanded underneath the photon's path. The invariant stays stable even while almost everything else about the situation keeps changing. Now, physicists genuinely disagree on what a null interval implies about the deeper nature of time itself, and there are 3 broad ways they've tried to make sense of it. And I'm going to give you all 3 without picking a winner, because none of them is ruled out by the data, and that matters more than which one feels satisfying. The first is the block universe view, sometimes called eternalism. Space-time in this picture is a single, fixed 4-dimensional structure, and past, present, and future all exist equally, simply different locations along the time axis. The way different cities all exist equally, even though you're only standing in one of them right now. Under this view, a photon's emission at the birth of the universe and its absorption in your eye today are both simply points embedded in that fixed structure, neither one more real than the other, and the null interval between them isn't strange at all. It's just a geometric fact about the shape of the block, no stranger than saying 2 points on a diagonal line sit a certain distance apart. This view has serious defenders because it fits the mathematics of general relativity extremely cleanly, with no privileged now anywhere in the structure. The second is presentism, the view that only the present moment is real, that the past has ceased to exist, and the future hasn't happened yet, closer to how human beings intuitively experience time by default. The trouble is that presentism sits awkwardly next to special relativity, because relativity tells us simultaneity itself isn't absolute. Two events simultaneous for one observer can happen at genuinely different times for another observer moving relative to the first. And if now isn't even the same set of events for two different observers, it becomes hard to say which now is truly real without picking a privileged frame, something relativity was specifically built to avoid. Interestingly, cosmology hands presentists something special relativity alone doesn't. The cosmic microwave background provides a natural, physically motivated rest frame for the universe as a whole, and our solar system's own motion relative to that frame has actually been measured through a subtle asymmetry in the background radiation's temperature across the sky. Some presentist-leaning physicists point to this as a legitimate candidate for a preferred cosmic now, arguing it isn't arbitrary but something the universe itself seems to supply. Critics respond that a frame being observationally convenient for describing the average motion of matter isn't the same as being fundamentally privileged in the laws of physics themselves, which remain stubbornly identical in every frame, that special one included. The debate hasn't resolved, and it isn't going to resolve from a video, but the presentist position isn't simply grasping at nothing. The third is a more cautious instrumentalist position, one a growing number of working physicists actually prefer, even if it's less exciting to talk about. This view says stop asking what time really is in some deep metaphysical sense, and instead treat the null interval purely as a mathematical structure that makes correct predictions. Asking what light experiences is simply outside the domain of what physics is built to answer. Physics tells you what will be measured, not what it's like to be a photon, and conflating those two things is a category error, regardless of which metaphysical picture of time you personally prefer. There's a useful historical parallel here. Early quantum mechanics faced a similar temptation, asking what an electron is really doing between measurements, whether it has a definite position the whole time or only becomes definite at the moment of detection. The instrumentalist response then, loosely associated with the Copenhagen approach, was to say the theory gives you the probabilities of measurement outcomes, full stop, and any further story about what's happening in between is metaphysics written on top of physics, not physics itself. That frustrated plenty of serious physicists, Einstein included, who spent decades searching for a more complete picture underneath it. The parallel isn't perfect. The null interval is a settled geometric fact in a way quantum measurement outcomes are still actively debated, but the instinct is the same. Draw a hard line around what the equations actually commit you to, and treat everything past that line as a separately arguable philosophical project. None of these three positions is proven wrong by any experiment we currently have access to. All three reproduce exactly the same observable predictions, because they're interpretations layered on top of the same equations, not competing equations. This isn't a case where one side has the data and the other is in denial. This is a case where the data genuinely underdetermines the philosophy, and anyone who tells you with total confidence which one is actually true is selling you certainty the physics itself doesn't provide. Here's where I'll step slightly outside the strictly provable, and I want to flag clearly that I'm doing it, because that line matters. If you ask me personally which of these three pictures feels most consistent with everything else we know, I lean toward treating the block universe view as the most mathematically economical. Not because it's proven, but because it requires the fewest extra assumptions bolted onto general relativity to make sense of a universe with no privileged simultaneity. That's a philosophical preference, not a physical conclusion. And there are serious, credentialed physicists who'd push back on that preference for good reasons. I'm not asking you to adopt it. I'm telling you where I land, so you know the difference between what I've shown you and what I merely believe. Research in quantum gravity over the past several years, particularly work trying to reconcile general relativity's block universe-friendly structure with quantum mechanics' apparent need for a well-defined now at the moment of measurement, has kept this question genuinely alive rather than settled. Some approaches to quantum gravity treat time as emergent, a higher-level phenomenon arising from correlations between quantum systems rather than a fundamental ingredient of reality at all. If that turns out to be right, the question of what a photon experiences gets stranger still, because you'd be asking about the behavior of something within a framework where time itself isn't fundamental to begin with. That research is nowhere near finished, and no consensus has formed, but it's worth knowing this isn't a closed book. Bring this back down to something you can actually hold on to. Every time you look at anything, you're receiving a signal that has, by every reference frame you could possibly occupy, taken a measurable amount of coordinate time to arrive, and yet is, by the geometry of its own path, separated from its origin by an interval of exactly 0. Both facts are true simultaneously, and they don't contradict each other because they're answers to two different questions asked in two different frameworks. The discomfort you might be feeling right now isn't a sign you've misunderstood something. It's a sign you've correctly understood something that genuinely doesn't map onto human intuition. Intuition built for a world of slow-moving objects and unambiguous simultaneity, never for a null geodesic. This is also, if you think about it, a doorway into a broader question worth carrying with you. What observation actually does to a physical description, and how much of what we call reality depends on the frame you happen to be measuring it from. The measurement problem in quantum mechanics asks a version of this same question at a completely different scale. Does a quantum system have a definite state before it's measured? Or does measurement itself play a role in bringing a definite outcome into being? The null interval of light and the ambiguity of quantum measurement aren't the same puzzle, but they rhyme, and both show you a place where the naive picture of an observer-independent, universally agreed timeline of events quietly breaks down under close mathematical scrutiny. Before you go, 3 quick things. First, save this video because dense material like this, proper time, null geodesics, 3 competing interpretations of what time actually is, doesn't fully land on a single watch, and you'll likely lose the majority of the specific details within about 48 hours without coming back to it. Second, subscribe, because this channel builds these ideas in sequence, and the next video picks this up directly, applying the same rigor to the measurement problem in quantum mechanics, showing the math separated clearly from the interpretation, refusing to pretend more certainty exists than actually does. And third, tell me in the comments which of the 3 interpretations, block universe, presentism, or the instrumentalist position, you find yourself drawn to, and why. Genuine disagreement, not performed disagreement, is exactly the intellectual work this channel is built around. Drop your location too. I read every single comment. I want to know exactly who's watching this from where. There's a temptation, once you've absorbed something this disorienting, to want it to mean more than it does, to turn a null interval into a life lesson, a reason to feel small or enlightened. Resist that pull. The value of this fact isn't in how it makes you feel. It's in what it demonstrates about the limits of intuition when intuition is asked to operate outside the narrow range of speeds it evolved to handle. If this changed how you think about the light reaching your eyes right now, a like and a share help this reach someone else who'd want that same shift.